Now it is section 5.2, classification via logistic regression. Logistic regression is a probabilistic model. The algorithm maximizes the likelihood of the parameter W. However, in its realization is quite similar to Adderline. The only difference is the activation function as shown in this figure. Adderline uses the identity function for activation, while logistic regression uses the sigmoid function for activation. So the prediction, the output of the sigmoid function, can be interpreted as the probability. Once phi is the sigmoid function, then output will be between 0 and 1 for the net input z. So that can be interpreted as probability that the sample x belongs to class 1 given weight w. Logistic regression can be applied not only for classification but also for class membership probability. In prediction, we may apply thresholding to get 0 or 1. That's for classification. However, without thresholding, we can use the output of the activation to show probability of a certain event. For example, logistic regression is used in weather forecasting to predict the probability of rain. Similarly, it can be used to predict the probability that a patient has a particular disease given certain symptoms. That's the reason logistic regression is quite popular in the field of medicine. Now we'll drive logistic cost function. Logistic regression incorporates a cost function in which the likelihood is maximized. Now we begin with some definitions to get a cost function for logistic regression. The binomial distribution with parameters n and p is the discrete probability distribution of the number of successes in a sequence of n independent experiments. Each experiment is asking success or failure. The probability of success is p. The probability of getting exactly k successes out of n trials is given by this equation. For one case, we have that probability, and there are k success. So k, for all k of them, it should be success, and for remainder, and n minus k must be failure. The probability is 1 minus p, so that one case it has such a probability. However, there are many cases. In fact, the number of cases is given in this term, n combination of k. So we have to multiply this integer to get the probability. Now we define likelihood. Let x1 to xn have a joint density function f, and given the values, and the function of theta, the parameter, is defined in this way, is the likelihood function, or simply we say the likelihood. Along with this definition, it's not clear to understand likelihood. So I'll try to explain a little bit about the likelihood. The likelihood describes the joint probability of the observed data as a function of the parameters. The likelihood function indicates which parameter values are more likely than others, in the sense that they would give the data more probable. So the maximum likelihood estimator selects the parameter values, in our case now W, that gives the data the largest possible probability. So here in logistic regression, we try to find the W that makes the data the largest possible probability. Here we'll derive logistic cost function. We start with the assumption that the individual samples in the data are independent of one another. Then we can define the likelihood in this way as a product of probability from each sample. So that can be maximized when, if here the Zi is net input from Xi, the Zi, phi Zi is around 1 for label 1, and now phi Zi is around 0 for label 0, then the value will be large. So in that way, we try to find W to maximize this likelihood. However, in practice, it's often we try to apply a logarithm to get log likelihood. After taking logarithm, we can get here this equation. The product is changed into summation, and the power is simple multiplication. Here for log likelihood, we have here the comment. Firstly, applying the log function reduces the potential for numerical underflow. These are probabilities, and if you multiply the number between 0 and 1 many times, in fact, the same as the number of the data points, then it can be small. So we can have numerical underflow by taking logarithm so that it changes into summation so that underflow can be reduced. Secondly, now rather than original likelihood, if you consider log likelihood, then you can use derivative, the calculus technique, more conveniently and much easier to get derivative. So we try to use log likelihood. And we have to maximize this log likelihood, but rather than itself, we try to multiply -1. So negation of the log likelihood will be used as the cost function for logistic regression. So here, logistic cost function is defined in this way. There is a negative of the log likelihood. And JW, as a function of W, now the cost function is defined in this way. Here, when YR is 0, the XI is belong to the class 0, then now this term will be 0 and only this term remained. And for the other case, when YR equal 1, then now this will be 0, so that we have only this term. Here, we'll consider the extreme case when n equal 1, only a single sample. Then the sample, if the sample is belong to class 1, then the objective function, cost function will be given in this way, and also in blue curve that is made. And for the other case, y equals 0, then we have the orange, the curve here. So if we focus on this case, the solid curve in blue, then now here once it is wrong classification, like in the probability is around 0, then object function value is very large, so that it push W so that the probability will go down. So the minimum value is happening when the phi z is 1. And the other case also can be considered similarly. Once here y equals 0, then now is wrong prediction, then cost function is very large, so that the algorithm will push so that eventually the probability will go down to become 0. Okay. Here so that the main idea is, if it is wrong, then we penalize wrong prediction, so that the algorithm is now enforcing the model to fit the sample. So for many general sample size, and here now the algorithm is trying to fit all the samples in the training data set. Okay, now we consider the gradient descent method. So we start with the derivative with respect to the parameter and chase weight wj, then we can get that one. For this term, now by using the chain rule, we can get this one, and we already know that for sigmoid function, its derivative is same as sigmoid function times 1 minus sigmoid. And we have that, and the wj derivative of zi is just xj. So we put over there, then we can write in this way, and because of that portion appearing here, so that that can be changed into, with multiplication with that can be changed into 1 minus phi, and this portion is changed into phi. So we have that here. Okay. So with simplification, we reach at that. So in vector notation, we end up with this one. The gradient descent method is taking negative of that one and scaled by eta. So in the gradient descent rule for delta W, we have now eta times sigma of this portion. And that is now the same shape as that of the other line. Only the difference is, rather than identity function, we are using sigmoid function. That's the only difference from the other line rule. Okay. Okay, we'll continue in the second part of the section. Thank you.